The Sun just hurled 3 massive blasts of plasma directly at Earth, crashing into our planet's magnetic field while it was already supercharged from a rare 72-hour geomagnetic storm, the strongest since March. In that same window, a magnitude 6 earthquake erupted off Japan's coast, raising urgent questions. Can cosmic fury and seismic upheaval be more than a coincidence? October is barely underway, yet energy is erupting from the Sun, ricocheting through space and shaking the ground beneath our feet. But with a full moon and even more solar waves about to hit, are we about to see a chain reaction unfold? NOAA's Monitoring Center clocked the storm's duration at almost exactly 72 hours, 3 days of relentless magnetic turbulence, with the K-index holding at G3 levels for much of that window. That's the longest run of elevated geomagnetic activity since March, and it didn't go unnoticed. During the peak, electron flux in the outer radiation belts shot up by more than 10 times the usual background, flooding the magnetosphere with high-energy particles. Auroras spilled south well past their usual boundaries, lighting up skies as far down as 40 degrees north. Power grid operators in Japan and across the northern hemisphere switched to storm protocols, logging minor transformer surges and watching for the kind of current spikes that can trip entire substations. Satellite controllers reported increased drag and a handful of minor system resets. Nothing catastrophic, but enough to keep teams on alert. What makes this episode stand out isn't just the storm's strength or length, but the timing. The full moon is about to sweep through Earth's magnetotail, a path that's known to stir up electric field gradients and nudge plasma flows. This lunar alignment acts like a cosmic amplifier, stacking on top of the magnetosphere's already supercharged state. With the system loaded, even a small push could trigger outsized effects, from dazzling auroras to subtle ground-level disturbances. As the Sun fires off another volley of plasma, the Earth is sitting primed, tension building in the sky, and some argue, beneath our feet. A coronal mass ejection, or CME, is a giant bubble of magnetized plasma that erupts from the Sun's outer atmosphere and races through space. When a CME is aimed at Earth, it can slam into our planet's magnetic field and trigger what scientists call a geomagnetic storm. These storms are ranked by strength using the NOAA-AG scale, which runs from G1, or minor, up to G5, which is considered extreme. The recent event reached G3, strong enough to disturb power grids, create auroras far from the poles, and disrupt satellite operations. Now, not every CME causes a storm this intense. The impact depends on the speed, density, and magnetic orientation of the plasma as it arrives. If the CME's magnetic field lines up just right, especially if it's pointing southward relative to Earth's field, the energy transfer ramps up fast. That's where the Russell-McLaren effect comes into play. Around the equinoxes, Earth's tilt lines up the geomagnetic field in a way that makes it easier for solar wind energy to pour in. This is why March and September often see the strongest storms of the year, even if the Sun's activity isn't at its peak. During these windows, the magnetosphere acts like a loaded spring. A well-timed CME can set off a chain reaction, charging up the radiation belts, lighting up the ionosphere, and pushing the entire system toward a more unstable state. With the right alignment and enough energy, even a moderate solar blast can have outsized effects, both in space and down here on Earth. The official record from the USGS reads almost like a checklist. On September 30th, as the G3 geomagnetic storm peaked, the planet's stress gauges ticked upward. Just over 24 hours later, at 10:25 UTC on October 1st, a magnitude 6.9 earthquake ruptured beneath the Mindanao Trench in the Philippines. Event YDUS 6000 REIE. The next evening, October 2nd at 1955 UTC, another strong quake hit south of Sumba, Indonesia, measuring magnitude 6.0 at a depth of 47 kilometers. That's USGS event, US 6000 REMK. And again, no tsunami, but clear ground movement logged across the Banda Sea. Less than 24 hours after that, on October 3, 1906 UTC, a magnitude 6.1 earthquake shook the Kamchatka Peninsula, event IDUS 6000 REM6, striking a subduction zone known for deep, powerful ruptures. Then, on October 4th, at 1521 UTC, the sequence continued off the coast of Fukushima, Japan. This was a magnitude 6.0, 47 kilometers deep, officially catalogued as US 6000 RESN. Local time, it was just past midnight, and millions felt the tremor, though no major damage was reported. What stands out is not just the magnitudes, but the rhythm. 4 major earthquakes in 4 days, all clustered along the Pacific Rim, each one recorded within a narrow window of heightened geomagnetic activity. The catalog entries are clear, the timing precise. While the USGS maintains that tectonic forces are the main driver, the temporal overlap with the storm's peak invites closer scrutiny. The question is whether the Earth's crust is simply responding to its own internal pressures, or if these external surges, tracked in real time by space weather monitors, are nudging the system when it's already on edge. GOES. 16 satellite logs from September 30th through October 4th show electron flux in the outer radiation belts rising more than tenfold, with peak readings in the 2 mega-electron-volt channel jumping from a quiet time baseline of about 300 particles per square centimeter per second to over 3,000. These numbers aren't just statistical noise. They reflect a magnetosphere saturated with high-energy particles, the kind that can disrupt satellite electronics and even force operators to adjust orbits. Low Earth orbit satellites especially reported increased drag during this period. Several commercial operators logged unanticipated orbital decay, requiring minor course corrections. At least 2 minor system resets, so-called single-event upsets, were linked to this surge in radiation belt activity. Ground-based magnetometers in Japan, including the Kakioka station, recorded sharp swings in the horizontal magnetic field. On September 30th, the H component dropped by almost 280 nanoteslas within hours, with rapid minute-by-minute fluctuations continuing for days. These are not everyday background wiggles, but clear signatures of a geomagnetic system under stress. Local utilities flagged minor transformer current surges, and ionospheric sensors picked up density spikes that matched the storm's main phase. This isn't the first time such a pattern has played out. In March 2025, a similar strong geomagnetic storm saw GOES electron flux spike 14 times above normal, while ground stations in Japan measured magnetic field deviations exceeding 300 nanoteslas. Within that same storm window, a magnitude 6.5 earthquake struck Myanmar. The sequence of satellite anomalies, ground perturbations, and seismic activity drew attention from both space weather forecasters and seismologists. While mainstream science remains cautious, the multi-layered signals from space and ground instruments suggest a system that, at times, operates right at the threshold, primed for outsized responses to even subtle nudges. Dr. Susan Hauch at the USGS puts it plainly: there's no compelling evidence that solar storms cause major earthquakes. Statistical clusters do show up now and then, but when you zoom out to larger data sets, those patterns tend to dissolve into background noise. Most seismologists point to tectonic stress as the main driver, with timing overlaps between geomagnetic storms and quakes chalked up to coincidence. On the other side, researchers like Dr. Sergei Pilipenko argue that, in rare cases, strong geomagnetic induction could nudge a fault already near failure, especially in highly conductive zones. But even proponents admit the effect, if it exists, is subtle and hard to pin down. Agency statements from USGS and ESA are careful. They acknowledge the debate, but emphasize that correlation does not mean causation. Much of the real-time geophysical data remains proprietary or incomplete, limiting what can be tested. For now, the mainstream view remains cautious, focused on what can be measured rather than what can be imagined. Forecast puts 3 separate plasma waves on a direct path for Earth between October 7th and 9th. The official guidance calls for G1 to G2 geomagnetic storms, which means the KP index could spike as high as 6, enough to light up the aurora oval deep into the mid-latitudes. If you're in Minnesota, Scotland, or northern Japan, there's a real shot at seeing the sky turn green or even red, especially during local midnight hours. Operators in aviation, power grids, and satellite control centers are on high alert for increased drag, brief radio blackouts, and possible GPS errors. Both NOAA and the UK Met Office models agree. The greatest risk window falls midday on October 8th, when the second plasma front is expected to hit. All eyes are now on real-time data streams. Every reading could be the difference between a quiet night and a global display of geomagnetic power. Between September 30th and October 4th, 4 major earthquakes, each above magnitude 6.0, were recorded in the Pacific region, coinciding with a G3 geomagnetic storm confirmed by NOAA and a greater than 10-fold surge in GOES-16 electron flux. Historical data show that similar stormquake overlaps have occurred before, such as the March 2025 Myanmar event, but no definitive mechanism has been scientifically proven to link solar storms to seismic triggers. Key agencies, including NASA and the USGS, agree. While the timing and energy transfer through Earth's magnetosphere and ionosphere are measurable, causation remains unestablished. The upcoming forecast, with 3 further plasma waves expected from October 7 to 9, is backed by official models and could bring G1 to G2 level impacts and widespread auroras. What remains unknown is whether these cosmic forces influence earthquakes, or if their alignment is coincidence. What is certain, documented by satellite, seismograph, and forecast, is that Earth's environment is more connected and dynamic than ever recorded.